Hey guys, today we're going to be screencasting the educational Codeforces round 93. Yeah, past experience tells me I'm not going to enjoy this, but we're doing this for the views anyway, so might as well get it over with. And I guess that's it. Let's get into it. Of course, I'll be doing commentary, just offering my thoughts and whatnot, as always. And we'll see how it goes. Just check the OBS again. Okay, perfect. It says we're recording. It's always a good thing. Let's begin. Okay. Okay, so degenerate triangle basically has the longest side must be longer or at least as long as the sum of the two other sides. When I explain the problem, I'll use some diagrams for that. So if but anyway, since it's sorted, we might as well take the smallest two for the sides that we want to be small, and then the largest one for the one that we want to be big, since it's basically greedy. And what? It is impossible to construct a non-degenerate triangle. Oh, wait, okay. Maybe we might have misread that already. Okay. Second test case, you can always construct a non-degenerate triangle. Oh. Okay, in that case, we want these to be as close as possible, so we'll just check every pair of consecutive things. Yeah. That was kind of a misread. I kind of thought that the problem was the opposite, but whatever. 4i m minus 2. We'll just check ai. C out plus 1. And return. Test that again. Okay, what? Wait, what am I doing here? Was I right the first time? What am I doing? Oh, wait, okay. I think I messed up my initial condition. So I did actually read the problem correctly, but yeah. So we want it to be, forced to be degenerate, I guess. That was a bit stupid. Guess I can explain what my mistake was there, but later on. Yeah. Let's just solve problems for now. And binary string S, consecutive equal characters. And they want to remove as many ones as possible. Okay, so if you're going to remove a 1, you might as well remove a whole block. Let's see how this works. questions about the optimal strategy will be ignored. Okay. That is quite fair. So I guess, is there any reason to remove a 0? No, because that just gives your opponent a better move. So you want to remove a 1 at every turn, and in every turn you want to remove the biggest like run of 1s, like the biggest consecutive group that you have. So we'll just make a thing of groups, then 0. So we'll just first put all of the groups into a vector, and then we'll just sort them in reverse order and take what we can for Alice. For in, if r is greater than 0, if si is equal to 0, and the last one isn't 0, then groups.pbr, then r equals 0. Otherwise, increase the size of the group of 1 that we're at, then sort groups.rbegin. That will sort them in reverse order. Also learn to type. We increment by 2 because Bob can always take like the next biggest ones. And that should be it. What? What? What is that? Maybe we're counting the zeros too. How does that work? How do we have 5? Oh wait. If r is greater than 0, if r is greater than 0, groups.pbr. That shouldn't actually make a difference, but how does this happen? 5, 2. Else if si is equal to 1. Right, okay. Obviously we don't want to count zeros, that's a bad idea. 4066. Let's get rid of the debug. Try that again. Okay. Sweet. Luckily we didn't need to ask any questions about the optimal strategy, like asking how to solve the problem. Okay, good subarray. Subarray is good if the sum of elements is equal to the length. For example, if a equals 1, 2, 0, then there are 3 good subarrays. Calculate the number of good subarrays of the array A. Okay. So how do we do that? Wait, digits? Why would they do it like that? That is a really weird way to do the input, but okay. Let's see, and s for in ai equals si minus 0. This will convert each character to its actual digit. So, what? Why would they do it this way? This doesn't really make sense. I'm thinking, so we can fix the, let's say, right endpoint of the array, then It's kind of like an offset problem, I guess. So we fix the right endpoint of the array. Let's use an ordered set so we can, no, not that, just this. There's probably a way to do it without this, but this is the most convenient option. So I'm just, oh wait, we don't even need that. We can just use a map. Okay, map, hello, count, then for in. Okay, plus count AI plus I, and it's plus equals count I plus 1. This is, I think, if this works, it's a bit cryptic. I'll explain where this comes from later. It's kind of the idea of using an offset, so we don't have to, so essentially everything is treated equivalently. Okay, well, it's wrong, so that's fair. Why is it wrong? For LLX count should be pair. I have a macro for printing pairs, so that's fine. Why? 1 1. What? Why did I click on that? 1 1 1 1 2 0. Oh wait, okay, we kind of screwed that up, didn't we? Yeah, we did. Okay. So it should be like something like offset equals 0. Then how'd this work? Offset plus equals AI. Zero. Okay, that's not helpful. Why does that happen? So we have 0 0. Maybe it's here. Doesn't actually make sense. Probably shouldn't work, but yeah, that makes even less sense. Okay. There is some smooth way to do this with some tricks, I think. So essentially the idea is we're going to subtract out the prefix sum. Before that, then, okay, yeah, that's the idea. So we subtract out the prefix sum. There's some order of these statements that work, so I'm kind of guessing it right now, but that's not right. Okay, let's get rid of that, because that's, can't even read that, so 2 1 0. Okay, so what happens is here RS becomes 1, then we add plus count 1, on account of that. And something is very messed up here. So we're going to subtract out the prefix sum, then add it back in. We want it to be equal to the size. So the size must equal the value minus the prefix sum. Which means, I guess here, we want this. I guess we subtract this because we want it to be 0. Not entirely sure. Okay, that also doesn't work. If we add this here, you can see kind of how sketchy this is. Okay, wait, so first we have the prefix sum here. Then first we have the prefix sum, so we'll subtract the prefix sum, and then also subtract the number of elements that are before it. Okay. This is still very sketchy. So we'll subtract, let's say we're here, we're going to subtract the prefix sum and also the number of elements that are before it. Is that right? Let's say we want the sum of the elements minus the prefix sum to be 0. So we're going to, maybe we add the number of elements before it. We have to subtract this somehow. There's a possibility that we might need to flip the sign on that. That's fine. Wait. Offset minus I minus 1. There's no way that this works. Okay. This is not a good way to do this type of problem. Generally, what you want to do is you want to work out an expression on paper. Like, for example, here we want, I'm not going to whip out paint yet. We'll save that for later. So here we want, like, for example, the index, I, length of the array, minus sum of elements equals 0. Then you can kind of put this position in a way that allows you to treat all of them the same, which is kind of what I did with the offset, and then you'll just count them, I guess. So let's submit this, get wrong answer, and figure out why. It's still very sketchy. Okay, guess not. Alright, so yeah, I'm going to have to explain this later, and also figure out why that worked later. But for now, we'll continue. Okay. Maybe that was easier than I thought. so we don't have test cases anymore. We're given 3 multisets of pairs of colored 6. Okay. First pair. Why would it be a pair? Oh, okay. You're constructing rectangles. Take a pair of sticks of one color. Take a pair of sticks of a different color. Then add the area. Oh boy. Okay. It's this type of thing. Can we just do this with greedy? It doesn't seem like that would be possible. So you would take 20 times 11 and then 19 times 8. So do we just... I don't get it. I do not get it. Do we just do some priority queue stuff? Okay, so the question is, does greedy work? And in what situation would it not work? That's also a question we can ask. Let's say we had some big case like 2, 2, 2, because that's enormous numbers, then I don't know, like small things, and then so we can take 2017 here. Okay, in that case it won't work, because then we'll want to, yeah, we'll prefer to match 15 with 20 and 15 with 20 than 20 with 20. So greedy, I don't think is going to work. This should be 1, 1. I don't think it'll work, but maybe there's some other way to do it. $200 is small. That is notable. So I guess 200 is very small, so I'm assuming it's some sort of DP on the number of sticks we've taken. I don't see why that wouldn't work. AI, wait, okay, maybe there's a smooth way to... No, I guess not. AI, BN, AI, CN. That should not be right. X, Y. I'm going to regret this later. But, not right now. Reverse. Sort them in descending order. Sort B equals Y. Reverse B equals Y. Then we'll define a function and we'll just set this to 0. K is equals 1 or -1. And this DP is the highest number of highest area you can get, having used this many sticks from the first, this many sticks from the second, this many from the third. Then ants equals max ants. Okay, now Alright, so now we'll just what do we do? I guess vector if a is greater than 0, mp. Wait. Okay, we have to change these variable names because my arrays are called A, B, and C. So wait, this is what I get, I guess, for being like this. So this would be A, I'm minus 1, 0. If. So then we copy paste this. J is greater than 0. This would be bj minus 1. And this would be ck minus 1. Sort all b. If b dot psi, alright, b dot r. We'll sort in reverse order again. If there are at least two things we can do, LL best equals 0. Actually, how about for I b dot size? We need to cast this long, I size minus 1, I plus 1 size. Then I'm running out of variable names here. Okay, we're gonna use, I guess, x and y since we don't actually care about those. LL ni equals I, and j equals j, and k equals k. Area equals vx dot first times vy dot first. If c equals and we'll just copy paste this. And best equals max best area plus rec ni and j and k. Then turn j k equals best. That was ugly. Surprised it compiled first try. Don't expect it to work, but okay. Thanks. Why does that happen? Alright, what happens here? I'm using too much memory? Does it crash my own computer? Okay, why would this be -2? What? Oh, wait, yeah, that makes sense. That is not good. 20? Okay, it actually worked. Wow. I guess it's such a tiny sample that it should be fine. 99. 372. Let's test it on my own thing. Make sure it's not just a dumb greedy. 600. Okay, let's submit. I can't say this won't get wrong answer, but I don't have a large test to try it on, so might as well. Test 9. Test 10. It's a lot of tests. Okay. Whoa. Jeez, that is... we have 2 seconds, so I guess that's fine. That. I mean, okay, it doesn't actually depend on the elements of the array at all. So if we have any max test, it'll be fine. And we'll stay close to that runtime. Okay, so I think hopefully that shouldn't be hacked because I don't think it's not that close to the time limit. And yeah, let's just continue. Polycarp plays a computer game yet again. In this game, I love games. What the hell is this time limit? What are the constraints? That's not scary. 2 times 10 to the 5th. Alright, so that suggests some scary thing like n log squared n already. Normal memory limit. Okay. There are 2 types of spells, fire and lightning. And doubles the damage of the next... Oh wait. Fire does X damage, lightning does Y damage, and doubles something. Okay. So I guess it's a query thing? Oh, I see. For example, suppose the already knows 3 spells, fire spell at power 5, a lightning spell at power 1, a lightning spell at power 8. There are 6 ways to choose the order in which you cast the spells. First, second, third. This order does 5 plus 1 plus 2 times 8 equals 22 damage. Okay. So obviously we want to double big things. That's the intuition. By the way, how are we doing? It seems not like great because yeah, we're not that fast, but okay. Didn't exactly speed force C. Okay, there's a single sample. It's not very nice. Oh, it can be negative. Oh, I see. Okay, so that's... Oh, wait, no. That just means he forgets it. Yeah, okay, good. What does that mean? So I'm guessing we want to start with a lightning spell and then... So each lightning spell will... Okay, this just looks like some messy implementation. Each lightning spell is going to double exactly one thing, and so there are a fixed number of things that can be doubled. Specifically, it's equal to the number of lightning spells, and we can't double all of the lightning spells. Like, we have to, like, the first one can't be doubled. But then once we use the first one, we can do whatever we want. And then the challenge, so if this were a simple problem, then if we didn't have to constantly recompute it, it would be very simple. We could solve an O of n, but we do. So we need to maintain the number of things we can do. So there are 2 cases. Either it's optimal to try and double all of the lightning spells, or it isn't. If it isn't, then we're happy. Otherwise, then we're not happy, I guess. These types of problems are, I don't know what to say about them. You just have to like do things. Okay, let's create 4 multisets. Set answer equals 0, and then we'll just print answer after everything. For in do magic. Alright, so we're gonna create 4 multisets. Actually, I guess that was 2. So then the first dimension is fire or lightning. Second dimension is doubled or not. So when you add or remove a new spell, I think it's true that only like only one, at most one spell is going to change from the state of being doubled to the state of not being doubled. So maybe that would be important. So in terms of implementation, we could do something nice about that. Okay, so first of all, int t if t equals 0. Are these distinct? Yes. The powers are different, so fine. So if x is greater than 0, then vowels if vowels 0 or t 0 dot find x vowels t 0 dot end. That means if it's in the set, vowels t 0 dot erase x. Actually, only need these sets, which is even nicer. Ants minus equals x. Else vowels doubled. We don't even need this. Dot erase x ants minus equals 2 times x. Wait, this should be if x is less than 0. Otherwise, ants plus equals x vowels t 0 dot insert x. Now, have an idea. So we're going to essentially just force ourselves to recalculate what's very close to the optimal answer, but not the actual optimal answer. So I will explain what that means later. I think this will work. I'm relatively confident about it. Dot size is greater than 0. Auto v equals vals 0, 1 dot begin. Ants minus equals v dot erase v 0, 0 dot insert. And we're going to put this first. If vals 1, 1 dot size. This way we don't have to do any sort of casework on what we remove. We'll just, it'll work out, I think. So then rec the number of things we have left to double equals what is it? So it's n doubled equals vals 0, 1 dot size plus vals 1, 1 dot size. Oh, rec equals vals. Let's just count the number of lightning. Vals 1, 0 dot size plus vals 1, 1 dot size. While rec is greater than 0, and we have something to remove, that is vals 0, 1 dot size. No, vals 0, 0 dot size. These are the fire spells. Or is vals 0, 1 dot size is greater than 1 because we have to have at least one lightning spell that's not doubled. What do we do? So int targ equals 0. If vals 0, 0 dot size is equal to 0, targ equals 1, else. This is so monotonous. Else, then we have something in both, so we have to check which one's better. A equals vals 0, 0 dot r begin. B equals vals 0, 1 dot r begin. This will take the biggest element. Then if A is less than B, targ equals 0, else targ equals 1, targ equals 0. Then vals vals 0 auto it equals vals 0, targ 0. Wait up. Oh, I've messed this up. Oh boy. Okay, so these should all be 1, 0 because this is lightning and not yet doubled. Yeah, I've messed this up. Okay. So vals targ 0 is right. Let's just actually make sure that we've done this right everywhere else. So if lightning doubled is greater than 0, then lightning not doubled, insert lightning doubled dot erase. Okay. And this is not lightning doubled plus lightning doubled. This is lightning not doubled plus lightning doubled. Okay. So actually we can get rid of these, but it doesn't really matter. That is weird, actually. Auto it equals vals targ 0 dot r begin. Ants plus equals it vals targ 0 dot erase it. Okay. So how many seg faults do you think we're gonna get here? Actually, yeah, okay. first of all the compile errors because STL always does that. So line 130. Values targ 0.erase. What? Oh wait. I guess we'll make it the value. Okay. So let me guess. Segfault. No, it's just wrong. Sweet. Why? Why does that insert things? That should not happen. What? See how it's end up. Why does that happen? So 5, should still be 5. I hate that it does this. Okay. Gonna get rid of the endos then, because that actually matters. So 5, 5. Okay. 15, 25, 35. Wait, that. Oh, shoot, because x is negative, so we want to subtract that, right. Okay, but that still causes problems. Yeah, it's still wrong somehow. Why is that still wrong? Because what happens here is that we forget the spell that lets us doubles, so, okay, we'll do that. So 1, 5, 2, 5, 1, 15, 2, 15, 1, 15, 2, 15. What happened there? Wait, what? Okay. That doesn't help. Why is this doubled here? So, vowels 0, 1. What? Yeah, that is important, that we actually move it. Yeah, okay, good. So maybe that should fix things. It does not, okay. 5, 12. How's that become 5? I am so confused. Okay, I mean, somehow we lost this. We're going to print what's not doubled. Even though it's going to say doubled. Okay, so this is still here. Why is it still here? Oh my god. Honestly, I just need to, yeah. Because I'm looking for a negative element in a set with all positive elements, so obviously it's not going to find it. Let's see if that fixes things. Indeed it does. Okay, is there a bigger case I can use on this? Like, let's just test some more edge cases, like 5, 1, 3, 1, 5, 1, 7, 1, negative 7, 1, 20, 1, 1. Okay, wait. So 3, double the 5 and the 7. Remove the 7, double the 20. 5, 0, 3. What? No. Run the program. 5, 0, 3, 0, 5, 0, 7, 0, negative 7, 0, 20. Don't crash. Good. 3, 15, 8, 28. Okay, let's see. Hopefully that works. Might time out, actually. Okay, we got E. How many people have solved this? Sweet. So we're doing slightly better now. Let's course geothermal. Wait, really? Wow. Okay. Second thread timeout. No, I got wrong answer. Seems like it struggles every round because of some Java stuff. Oh boy, that is a scary simple statement. Alice and Bob play a game. The game consists of several sets, and each set consists of several rounds. Each round is won either by Alice or by Bob, and the set ends when one of the players has won X rounds in a row. For example, if Bob won 5 rounds in a row and X equals 2, then 2 sets ends. Okay. You know that Alice and Bob have already played N rounds, and you know the results of some rounds. So compute the answer for all X from 1 to N. Okay. Cool. Time limit 2 seconds, N is 10 to the 6th. It's interesting because it kind of approaches the, kind of goes to the harmonic series thing. Like the answer, the total sum of answers is at most N log N. I guess does that mean anything? I'm not really sure. How are the solves on G? Is F the better one to go for? 29 versus 10. That looks terrifying. Let's go back to F. Also, is my rank slowly declining because of my speed forces? Yeah, it is. At least I don't have any penalties, though. I mean, so far. Some other people have done that. sets. Each set consists of several rounds. Each round is won either by Alice or by Bob, and the set ends when one of the players has won X rounds in a row. Example, if Bob won 5 rounds in a row and X equals 2, then 2 sets ends. Okay. Why am I reading that again? I just already read it. So let's say there were no question marks. Then what we could do is what could we do? We could, first of all, put everything into chunks, I guess, and then how would we do it if there were no question marks? Let's say we would, so we would group all the consecutive 1s and 0s together first. Make sure we're still recording. It's just another sanity check. So we group all the 0s and 1s together, and so the answer is initially n, and then at each point there are certain points where each chunk will kind of like decrease the amount of sets it contributes. And alright, now it's time to whip out paint. So let's say we have, for example, 3 1s in a row. So if x equals 1, it contributes 3. If x equals 2, it contributes the floor of 3 over 2, which is 1. And x equals 3, also 1. Then x equals 4. Actually, x is greater than or equal to 4, 0. Write 4. X is greater than or equal to 4 leads to 0. So the interval when n over I is equal to x is on the interval which excludes n over I plus 1. I think this is right. This has always been sketchy for me, so maybe it's wrong, but this is what I think. And then the interval includes n over I. And the reason this works is because like the floor division of n over I is defined to be the greatest integer such that x is less than or equal to this. The greatest integer such that x is less than or equal to the actual value of n over I. So if we swap these two, then we get I is less than or equal to n over x. And at the same point, I is the greatest integer such that n over x is greater than or equal to I. So using that, we can essentially make it so what? So if we were to go any higher, then I would be increased by 1. But because I is defined to be the greatest integer such that this still holds, we can't increase it at all. And similarly, this is the greatest integer such that I plus 1 is less than or equal to n over x. So if we increase it by 1, then we're going to essentially step out of the previous interval and move into the current interval. So that's why this is exclusive, because it's the last element in the previous interval. I hope that kind of makes sense. It kind of doesn't make sense to me. I try to learn it so that it's intuitive, but it still isn't. But anyway, I think that's right in any case. So essentially what we do is we say at the point n over I. Oh wait, sorry, this should be n over x. This whole time it should be n over x and n over x plus 1. So then at the point of n over x plus 1, it will change. So for example, 3 over 2 equals 1 on the interval excluding 3 over 1. Wait, excluding 3 over 3, which is 1, and then including 3 over... Wait, no, that doesn't make sense. Sorry. Yeah, because I used the wrong numbers. This should be excluding 3 over 2, and then including 3 over 1, which, inclusive, which is the interval 1, 3, or the inclusive interval of 2 to 3. Yeah, so that's how that works, and then obviously it's 0, we can't divide by 0, so it's going to go on to infinity. So it would essentially be kind of like a priority queue or something, where we just compute the next point where it stops working, and then, yeah. Okay, so this long-winded explanation has almost nothing to do with the actual problem, since we also have question marks. So let's see, if we have a string like this, let's say 0, 0, dot, 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 1, 1, question mark, some number of question marks, 1, 1, dot, 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 whatever. Actually, these zeros don't even matter. It's the fact that we have question marks surrounded by the same number. Then, like, if we made these zeros, like, it's only going to hurt us. We might as well make these ones and then continue the interval. So the structure of our string is going to look like... And similarly, if we have question marks on the end, then like question mark, 0, 0, dot, 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 we might as well make these zeros. So really what we're going to have is we're going to have a string that looks like, for example, 0, 0, question mark, some number, question mark, 1, 1, question mark, dot, 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 question mark, 0, 0. Or maybe it'll start with ones. But the point is we have some number of zeros, or some number of ones, a question mark, some number of ones, question mark, some number of zeros, question mark, and these are alternating. 0, question mark, 1, question mark, so on. Wow, these look terrible. These don't even look like question marks, they're just like, I don't know what they are. I really need a writing tablet at some point. So that's what the string's going to look like, and so here, for example, we can make the whole string ones and it won't hurt us at all. So that's fine. So now essentially we just need to efficiently distribute the question marks among the rest. So if we were just solving this for 1, then we could do a greedy strategy. Like, let's say x was fixed, right? Then let's say x was 2. Then we have the string 0, 1, try and draw an actual question mark, 0, 1. And then x equals 2. So then we don't get any sets out of this. We don't get any sets out of this, but we have a question mark here. So what we'll do is we'll greedily attribute as many of these question marks to this one as necessary. That is, we'll try and make as many groups as possible. And then once we either make an exact group or we can't make any more, we'll stop and give the rest of the question marks to this 0, because that won't hurt us at all. since there's no point giving extra question marks to the one that we're not going to use at all. So that would be kind of like a greedy strategy. But the issue is we have to solve for all x. So either we have to optimize the greedy or do something smarter. And I'm not sure which. Another interesting thing is that the answer is at most the answer is fixed, kind of. Or the answer is at most n log n, because, well, I have a... There's a proof that the, you can prove relatively simply that the sum from I equals 1 to n of the floor of n over I is O of n log n. And in fact, it doesn't even have to be the floor. The sum of n over I in general, that's not an h, that's an n, is O of n log n. So the total answer will be O of n log n. So maybe we could kind of like ignore the things that are small. That is, how would that work? Like either there are a lot of groups or there are not many. And if there are a lot of groups, then there are going to be some small ones. And yeah, there are going to be some small ones. Wish the time limit was more nice, because then we could do some stupid solution where we only look at like groups that are of size x over 3 or something, because each... Maybe that's possible. Because if we have 3 groups together and all of their sizes are less than x over 3, all of their sizes are less... Let's say the size is y, and it's for some reason constant. Y is less than x over 3, then 3y is less than x, and therefore there's no way that using these groups will lead us to anything. So therefore, if we could process only the groups that have size that, then that's kind of interesting. What if we could do that? Would that work? I guess it would, huh? Yeah, I think it would. So we only process the groups that are of size at worst that. So first we're going to make the groups so we're going to use B as the starting position of each group. Let's see, R equals 0. So 4in, no, LL last equals 0. So if we're going to make these vectors of pairs, no, we don't need to. Do we? No, not really. Okay, so if Si is not equal to S last, then we have a new group. So n groups equals 0. Call that ng just to confuse our audience. So cng equals I minus last, that is the size of the group. bng equals last, that is any position that's inside the group. And should be it, I think. So we might as well use A as the size of the group. Then plus plus ng, last equals I. Now we need to do this again at the end. Or actually we can do s.pb, some character that isn't in the thing, like 7. Then, yeah, that'll work. So that will, let's just print AOANG, AOBNG. Let's just check if that works first. Two, 1, 3, 0, 2, 3. Yeah, that's right. So actually, before we even do this, we want to do some pre-processing to the string. That is, we want to make all of these question marks into ones, and all of these question marks into ones. So there should be some smooth way to implement this. I think there's something with 2 pointers, maybe. We want to test this. So for in, first of all, this is going to make the prefixes and the suffixes of the string the same. And we'll use the same implementation for them because it doesn't really matter. How do we do this then? Bool stop equals 0. If si is not equal to a question mark, stop equals 1, break. What? Why did we lose it? For ji, so we're going to set all characters before that question mark to si. Sj equals si. Then if not stop, we'll just set all of them to 0, for example. It doesn't matter which. And then, yeah. We'll set so that works. Test if it works here. Sweet. Okay, so that will work. Yep. And comp. Why do we recompile? 5. Boop, boop, boop. Okay. 5. 5. Question mark, 0, 1, question mark. That's it. Okay, sweet. And that does it. So now what we need to do is, for example, you saw when we ran it with this, it still has the question marks in between. So we want to make it so question marks in between two identical groups become filled in with the same thing. So I guess we can just use the groups for this. So for ing, then we're going to recompute the groups after. If s bi is equal to question mark, if s bi minus 1 equals s bi plus 1. And we can do this and we know it won't go out of bounds because we know that the ending groups are no longer question marks. So then for 1r I j bi b I plus 1. That will exclude bi plus 1. Sj equals s bi plus 1. That should hopefully work. Then what we're going to do is we're just going to recompute the groups since we've changed them again. Don't see why that won't work. Well, that might not, because why would code ever work? And it doesn't. Epic. But it actually it did the groups. Oh, because we're putting it here. Okay. Cout s and o. Now we should also have a 7 on the end, but that's not a big deal. I should give it the input. I think we messed something up there. Yeah, we gave it 12 as an input. So, well, 12. Perfect. Let's try that again. Shouldn't do anything to this. Shouldn't do anything to this. Let's give it 7. So question mark 0, question mark 0, 1, question mark, question mark. Yeah, it does. Okay. Let's give it 10. So question mark 0, question mark 0, question mark 1, question mark 1, 0, question mark. So these should be together, these should be together, these should be together, these should be together, these should not be together. And we're good. Okay. So now we have the actual groups. 0, 4, 5, and 8, length 4, 1, 3, and 2. Epic. So now I guess for I n c n g ci equals ci equals b. All right, sbi. We'll just use that to make it more clear. Then ao, c, and g. Also, we're going to use this as a sample because this is not a bad test case. So 0, question mark, 1, 0. Sweet. Okay, so now it took a while. Okay, so now we're going to weird. Now we're going to, again, we only have to check things that are greater than floor x over 3. So What we're gonna do is we're going to PLL. Just gonna call it V because I'm lazy. So for ing, vi equals mp, make pair size, and then I sort by size in decreasing order or increasing order. Then we'll create a set PLS. Since we don't need the actual string anymore, we can overwrite that. Wait, no, let's not make that mistake. For vi equals mp. Does it matter that if we have the size there? No, it doesn't. st.insert I. Then we're going to, I guess, for 1r, x, for x from 1 to n inclusive, ants equals 0. So, for, and we're also going to keep a pointer to this array, point equals 0, while point is less than ng, and v point, oh wait, actually first, LL, things to remove equals x over 3, so anything less than that will be removed, and vPoint.f is less than rem. st.erase vPoint.s. So we're going to erase the index from the set and then plus point, since we don't want to consider that one anymore. So this in total will take O of n, since the point only moves from the beginning to the end of the array, like a line. I open Paint to draw a line. And the set is at most size O of n, so it's n log n in total. For 10 to the 6th, that's, I don't know, kind of sketchy, but not really sure what we can do about that. I don't think anything. So there's a chance this whole thing times out and we have to constant optimize, so that's not going to be fun. So the reason that only checking things with size less than or equal to n over 3 works, I think, maybe it doesn't actually, is because what we're going to do is we're going to, it's the same kind of idea, the sum of, like at each point there are only the sum of n over I over 3. At each point, this is only, it's not bad. Like, there aren't that many. So, it's the same idea that we brought up before. This is equivalent to, let's say, 3n over I. Or it's not equivalent. I think 3n over I is an upper bound. I'm not sure. Anyway, it's close. So then we can take out the 3 from here. Yeah, it's not exactly the same, but it's pretty close. So then we have 3 of that equals 3 times something that's on the order of n log n. I really don't get why they had to make this 10 to the 6th. Probably to break this exact solution, actually. Because this seems kind of sketchy in terms of constant factor, but should be fine. So, for int y st. I don't know why we have int. Let's just make this long since we're submitting with 64 anyway. Like all of my submissions are using 64-bit. So, yeah. So for each thing, We actually only really care about the question marks, don't we? Because, let's see. Don't we? Because well, we'll only change things to the question marks anyway. So we're going to make a new array D, and we're going to mess with this array a lot. D is going to be the remainder that we have. So D, for example, dy equals ay. V equals dy over x. Then ants plus equals v, dy minus equals x times v. Wait. So we're just going to make this for convenience. If used y is greater than 0 and used y minus 1, dy plus equals ay, because we're already going to set this. Else, then this is alone, so dy is equal to ay. Keep in mind that this value of d could be filled with a garbage value from the last value of x, so we need to be careful to overwrite it instead of just adding things. So wait, if cy is not equal to a question mark, which means this is equal to a question mark since like they have to be alternating. Or wait, no, it doesn't. No, it doesn't actually. And cy minus 1 is equal to a question mark. And dy plus equals ay, otherwise dy is equal to ay. Then L of v equals dy over x. This will work, right? It'll be 0, 1. We're not going to ignore anything that's too big. No, we're going to do something else. We're going to do time. This is going to be fun. So time essentially means we've modified it in this thing. So let's say if time y is equal to x, then dy plus equals ay, otherwise dy is equal to ay. Then if time y minus 1 is not equal to x. Now if time y minus 1 is equal to x and it's a question mark, then we'll have used it already. And otherwise it's not. If time minus 1 is not equal to x, then dy minus 1 equals a y minus 1. No, wait. This should just be dy plus equals a y minus 1. C y minus 1 equals question mark. Actually, we should first check if y is greater than 0. If y is less than ng minus 1 and time y plus 1. No, wait. Automatically time y plus 1 is not equal to x, so should be plus. Then that doesn't matter because we're not going to touch it again. Time y plus 1 equals x. We don't actually need this. Because we'll assume if time y is not equal to x, then it was a question mark, and we've already used this. Okay. Y is less than ng minus 1, and cy plus 1 is equal to question mark. Time y plus 1 is equal to x. There's no way we're solving g, so let's just finish this problem. So then dy plus 1 equals a y plus 1. Dy plus 1 over x. Dy plus 1 minus equals b times x. Then what is it? We still have this whole else section to do where we have casework with question marks. Okay, so long rec equals what? It is x minus dy mod x. It's the amount we need to get another one. Then if dy plus 1 is greater than or equal to rec, dy minus equals to rec, plus ants, dy equals 0. Wait, actually, dy is already less than or equal to x, so that should be fine. Yeah, because we already do the mod basically here. If dy plus 1 is greater than or equal to rec, dy plus 1 is minus equal to rec, plus ants, dy equals 0. So let's just verify all this. So, case number 1, we haven't touched anything before it. And therefore, we just look here and set dy equals ay. Otherwise, we have touched something before it, and it has, let's say it's a question mark, then it's already set. We're going to assume that. So then, if we have a question mark before and it hasn't been looked at, then we might as well just take it. Otherwise, if it's a different value before, then it doesn't matter. Alright, okay, then we look at the next one. So if it's not a question mark, we don't care about, otherwise it is a question mark. So we're going to steal as many as necessary from that question mark. Yeah. Okay, so now we're at a question mark. This whole section is a question mark. So we do the same thing. If time y is not equal to x, dy equals ay, time y equals x. No, wait, time y is equal to x. Okay. And so now we have different values on both sides. So first of all, we'll just assume we can put this towards that. Then if time y, so if time y minus 1 is equal to x, then by this case we will have already used it. And we don't have to check if y is greater than 0 because question marks can't be on boundaries. So if time y minus 1 is not equal to x, then we will check some stuff. In particular, dy minus 1 equals a y minus 1. Then LOV equals dy minus 1 over x. That's plus equals v. Okay, now rec equals x minus dy minus 1. If dy is greater than or equal to rec, dy minus equals to rec minus equal rec plus ants dy minus 1 equals 0. That doesn't really matter, but we're going to do it anyway. So now we're going to push it to the top one. So now time y plus 1 is equal to x. Then dy plus 1 equals a y plus 1 plus d y. dy equals 0. Then we'll just do that. Okay. That was a lot of casework. So let's check it again. So this is a question mark. If we haven't looked at this before, set it to ay. Then time y equals x, fine. Then just put as many as we can towards the answer. Now if time y minus 1 is not equal to x, then dy minus 1 is equal to a minus 1. And the reason we do that is so we can... Maybe it sucks so much if I like misread this or something. Time y minus 1 equals not equal to x. Then we're going to put the requirement, or first we're going to process it. And if it's equal to x, then we can assume it's like we've already looked at it. And by this case, we can ignore it. So L of v equals dy minus 1 over x. Fine. Ans plus equals v. Fine. Yeah, we'll just do the same thing. So now it's less than x, so we can do this requirement thing. And we'll just give it to that if so. Then we'll go further, and we'll give everything we can to the next one, since we might as well. So, a1 plus 1. Yep. Perfect. Okay. Now comes the scary part. Try to compile it. Oh my god. Right. B. Is that it? There's no way that's it. What? Oh boy. Okay. We're gonna replace time with just some like other random variable. Replace replace. I think it's in STL, so we can't actually do that. Yeah, okay. Cool. Now what? Oh wait, we can just make these longs. Comp. Okay. Tell me this works. That should work. Assess it for this. I don't even know what the answer should be. Should be small though. So for example, this is 5, so we can have that. Then for 4, we can have this, then that one. Then for 3, we can have this, then that one. For 2, we can have all of them. For 10, we can have all of them. Okay, well I want to test it with some more, because this is not satisfactory. 17. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Question mark, 1, 1, 1. I don't know why we compile. Wait, what do we do? Okay, 17 obviously. So 2, 1, 2, 3, 4, 5, 6, 7, 8. Oh boy. Really? So 1, 2, 3, 4. Wait, hang on. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's good that we tested this then. And that we wrote the test down. Wrong thing. First, make sure the string is right. Oh, question mark. Okay. Now what? Is 2 the only one that's wrong? Let's see, we have 1, 2, 3, 4. Okay, and then for 4, we have 1, 2, 3. For 5, we have 1, 2. For 6, we have Oh, 6, we have that. Okay, and the rest, nothing. So what's happening here? If x equals 2, AO, D, and G. Well, it should be considering all of them, right? Wait, what is happening there? So it's O, O, O. Oh, wait. And O. Let's not be confused here. What? So O, 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 1, 1, O, 1. So O, 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 O. So that should be 4. Then 5. Wait, so 0, 1, 2, 3, 4. Why? Yeah, that's fine. That should be 1. This should not be 1. That's the thing. We should have considered this somehow. C, y plus 1. O time y plus 1 is equal to x. dy plus 1 equals ay plus 1. O of v equals d. Oh, wait. Okay. Okay. I see the issue. So we don't necessarily want to do this first. First we want to do is that. Yeah. So O time y plus 1 is equal to x. Then we're going to do the requirement first, then do this. Yeah. That's plus equals v, dy minus 1 minus equal. Dy plus 1 minus equals to v times x. And we don't actually need this at all then. Yeah. Okay. That will work because the issue here was that we were getting rid of these two question marks, so the better thing to do is to make this 0 and that one 1. So that would make it a better answer. So let's try that again, now that we got rid of that. And we get a compile error. Why do we get a v, LO? How do we print 7? What is in our register for that to happen? Should be 8. Still 7. Okay. Why is that still 7? L of rec equals x minus dy. If dy plus 1 is greater than or equal to rec, dy plus 1 minus... Oh, wait. Also important. Okay, now that works because, so we move this here, set O time, set D, check the requirement, then we get as rid of many of the question marks as possible. That will work. Yes, it will. Okay. Then here we do the same thing, so we're allowed degree do we take here first, that doesn't really matter. Then we set this, then we'll give everything to dy plus 1 anyway. Then we'll use that. Okay, so let's... Doesn't change anything else, right? 17, 8, 4, 3, 2, 1. Because we have 4 3s, 1, 2, 3, 4. We have 3 4s, 0, 1, 2, 3. 2 5s, 1, 2, 1, 6. Okay. We'll test with the given samples again. Cool. Still don't believe in this. Probably got some bit of casework wrong. Or it'll time out. That's possible too. Great. Okay. So we got through a lot of tests. How do we even do this? So we failed on a very big test since the time limit was big. I guess we'll just look over everything. I have no idea how to test this really. So void solve. Yes. Read in the thing. Convert the characters. So if SI is not equal to question mark, then stop equals 1, set everything to that prefix and be done. If not stop for IN, SI equals 0, then we'll just be done with that. S.pb7 for convenience, NG if SI is not equal to S last, ANG equals I minus last, BNG equals last, plus NG, last equals I, then we'll make the groups. For I to the number of groups, if SBI is equal to a question mark, then if the previous and the next groups are the same, then set all of these question marks to that value, because we might as well. Then make the groups again. We can just do that. Last equals I. Yep. And then for ING, CI equals SBI, that's convenience. For and G, VI equals MPAII, sort V plus NG, LO point equals 0. Set long set for ING S set insert I. MSO times 0. For x from 1 to m plus 1, ans equals 0, rem equals x plus 3. While we have things that are less than rem, don't do anything with them. I mean, get rid of them. st.erase v point dot second plus point. Okay. And for the rest of it, just print the answer. So I guess it's this. Unless there's some dumb typo that I'm missing. In which case you guys can scream me in the comments. So for each index in the set, if cy is not equal to a question mark, then if we've already messed with this value, set this to that. If we haven't messed with this value, then set this to that anyway. If y is greater than 0, and the last thing is a question mark, and we haven't messed with it, then just steal all of the things from the question mark, which is okay to do. Then greedily remove as many of the sets as possible. Then if y is less than the number of groups minus 1, and y plus 1 is equal to a question mark, then the next one is equal to a question mark. Then set the time to x. dy plus 1 is equal to ay plus 1. Yeah. Rec equals x minus dy. dy plus 1 is greater than or equal to rec. dy plus 1 minus equal rec. Plus ants dy equals 0. So we might as well just set the rest of them to that. And then we'll, yeah. Yeah. I think that part should be right, I guess. So if the time y is not equal to x, dy is equal to ay. So if we haven't messed with this before, so now that we're at question marks, so then time y is equal, set that to x. Then if we haven't messed with the previous one, because it's a question mark, we know it's some value, then dy plus 1 is equal to ay plus 1. Dy minus 1 is equal to ay minus 1. Then v equals dy minus 1 over x. Greedily take as many of those as possible. Then give 1 to that. Plus ants dy minus 1 equals 0. Then O time y plus 1 is equal to x. dy plus 1 is equal to ay plus 1 plus dy. dy equals 0. O of v equals dy plus 1 over x. Ants plus equals v. dy plus 1 minus equals x times v. dy plus 1 over x. Okay. Well, I don't really see an issue. So, I'm not sure what to do here. Let's try some random thing. Maybe if we make the groups bigger and try more things, it'll be better. And if this passes, then I'm definitely going to be hacked, so... So we're gonna get a wrong answer again. Okay. Alright, so glad that doesn't make a difference at least. Something wrong with the casework. Okay, well I don't think we're gonna be able to debug it in a minute, so let's see where we ended up. Alright, so I guess we'll explain things. Don't know what's wrong with my F. so I guess I'll explain what I did, but not, I can't guarantee that it's right. We didn't get G at all, so let's just not even think about that. Okay, so for A, what we do is we're given an array, for example, 4, 6, 11, 11, 15, 18, 20. Okay, so now we want to pick 3 indices. So for example, here, here, and here. And then you want to see that it's essentially impossible to create a non-degenerate triangle. So all triangles that you make will be degenerate with those sides, with those side lengths. So for example, 4, 11, and 18. So we'll draw one with side length 4, and we'll draw one with side length 11. But then 18 is like very long. So no matter what we do, like even if we do this, 18 is too long to be able to touch the other vertex. Like even if we make it touch, it will not form a triangle. So the condition for a triangle being degenerate is that, let's say we have the 3 sides x, y, and z, where x is less than or equal to y is less than or equal to z. If x plus y is greater than or equal to z, then there's nothing we can... No, wait, sorry. If x plus y... Wait, hang on. How does that work? If x plus y is less than or equal to z, my bad, then... Is that what I checked? Yeah, okay. So if x plus y is less than or equal to z, then there's nothing you can do, because z is just too long. If x plus y is equal to z, then like, even if you fold them in a straight, even if you make the edges in a straight line, z will also be like on a straight line, so it's not going to be a shape, it's just going to be a line. And that counts as degenerate, so there's nothing you can do about that. And if z is even longer than x plus y, then like no matter what you do, z is just going to extend past. So if this condition is true, then any triangle you create will be degenerate. So notice that we want this to happen. So we want x plus y to be as small as possible, and we want z to be as large as possible. We're also given that the array is in sorted order, which is kind of a hint. And all we have to do really is we'll take the 2 smallest elements for x plus y, and we'll take the largest element for z. And that works because we want to minimize this and maximize this. So all we have to do essentially, you can see how simple the code is since n is greater than or equal to 3, there will always be 3 elements. So we check if the first element plus the second element is less than or equal to the last element. If so, print these indices. Otherwise, no matter what, this will be at least as big and this will be at least as small, so we can't make this happen. So otherwise, there's no answer. So yeah, essentially we just check the first and last indices, and the first 2 and the last indices. Okay, let's go over B. In B, you're given a binary string, for example, 0, 1, 1, 1, 1, 0, 0, 1. And you're playing a game. In each game, in each turn of this game, you can pick some contiguous substring of characters. For example, a substring that has to be all together. And then if all the characters are all the same, you can remove it. So you can't remove this one because they're both ones and zeros. You can remove this one because they're zeros, and you can remove this one because they're ones, for example. And in each turn, you can do this exactly once, and you get a point for every one that you remove. If you remove a 0, you get nothing. But if you remove this, you'll get 3 points. If you remove this, you'll get 1 point, this 1 point, this 4 points. You can assume both players are playing optimally to maximize their own score. So you want to find the score that Alice gets given that both players play optimally. So essentially there's a greedy strategy for this. Each player will always remove the largest sequence of ones that exists. Because if you remove a 1, you might as well remove all of them, otherwise you're giving more to your opponent. And if you remove a sequence of zeros, then you're just giving your opponent a bigger sequence of 1s. So you don't want to do that. So you always want to remove a 1 if there is one, and if so, you always want to remove the biggest one. So you can essentially simulate the process. For example, in this one, the first one to be removed is 4, the second one to be removed is 1. Let's take another sample. For example, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1. Right? So there's a 4 here, a 3 here, and a 2 here. So Alice is the first player. So she's going to remove 1, and then Bob, the second player, is going to remove 3, and then Alice is going to remove the 2, and her total score is going to be 6. And for this one, Alice will remove the 4, Bob will remove the 1, and Alice will have to remove the zeros, and then the game will be over. And the zeros don't matter. So essentially that's it. You just check. The way to implement it is you group all the ones together using some like 2-pointers technique or something, and put them all in an array, sort it in descending order. That means the biggest elements are close to the beginning, and then just sum all the elements at even indices, because Alice is going to take, for example, the first one, the third one, the fifth one, the seventh one, etc. And with 0 indexing, it's going to be index 0, index 2, index 4, index 6, ... So that's all you need to do. For C, oh boy, this one. This one gave me kind of a struggle, to be honest. C, you're given a string with characters from 0 to 9, and it's basically an array, but it's given to you in a string format for some unknown reason. I don't really know why, because this condition isn't that necessary. Maybe there's an easier way to do it that hinges off this, but I don't really know. My solution works for the general case where like array elements can be anything, for example, up to 10 to the 9th, or even negative. So what you want is you want to find the number of subsequence or sub arrays. That means contiguous, all the elements are together. So for example, let's take the first sample 1, 2, 0. And you want to find the number of subarrays such that their length is equal to their sum. So for example, this is length 1 and has sum 1. This is length 3 and has sum 3. This is length 1 and has sum 0. This is length 2 and has sum 3. And this is length 2 and has sum 2. So the good subarrays, the ones that have sum equal to length, are this one, and this one. And you want to count those and print the number of them. So essentially what you can do is, this is the same as asking sum minus length equals 0. So now I have to figure out how to explain this, and don't really know how to explain it. I also don't know what I did. So yeah, that's fun. The general idea is we're going to use a map to store essentially prefix sums. Like the trick let's say we had an array like 3, -1, -2, 5, and we want to count the number of subarrays that have... Oh. Okay, I just realized something that's simpler. So, alright, we could have implemented that instead, but that's fine. So we're given an array here, and we want to count the number of subarrays that have total sum 0. For example, here, this one has 0, and that's the only one. So what we do is we would compute the prefix sum, which is the sum of all elements from 0 to I. So for example, 3 is the sum of 3, 2 is the sum of 3 and -1, 0 is the sum of 3 and -2, and 5 is the sum of all of these. So this would be the prefix sum array. Then, if we stuck another 0 here for like the beginning of the array, for example, then what you realize is that any subarray that has any subarray that has sum 0 has the same prefix sum at its beginning and its end. So let's get a different example, for example. So we'll So we'll have -1, 1, -2, 1, 1. Okay, then we'll compute the prefix sum. So we'll start with a 0, -1, 0, -2, 1, 0. Alright, this should be -1. So now, if you'll see that this subarray has sum 0, and its prefix sum is the same as this, and this subarray has sum 0, and its prefix sum is the same as this, and this subarray also has sum 0, and its prefix sum is the same as this, and same for this. So essentially, what we can do is we can group all prefix sums together. So we have, for example, 3 times 0, and 2 times -1, and 1 times -2, right? So then, we want to find the number of ways to pick 2 of these, to pick, for example, 2 zeros. And each number of way to pick 2 zeros is a subarray. So it's essentially just the number of pairs of zeros that we have, which is equal to n choose 2, which is well known to be n times n minus 1 over 2. So to count the number of subarrays with sum 0, it would be 3 times 3 minus 1 over 2. So for example, 3, the value of this is 1, and the value of this is 0. You can work that out for yourself. Then it's the sum of all those, so we have 4 total subarrays with sum 0. Okay, why is this helpful? Because let's write out the sum minus length as an expression. So this isn't actually the solution I implemented. What I did was kind of more complicated, but this is very simple. So let's do the sum of AI. Like, for example, sum from L to R of AI, which is equal to sum, minus R minus L plus 1 is the length equals 0. Now let's convert this equation. So each element contributes exactly 1 to the length, which means this, different color, this can actually be rewritten as, for example, the sum of from L to R of 1, because each element contributes 1 to the length. So if you see what I'm getting at here, now we do the sum from L to R of 1 equals 0. Let's combine the two sums. Sum from L to R of AI minus 1 is equal to 0. That's it. That's our condition. So if we subtract 1 from every element in the array, then we're just asking for the number of subarrays that sum to 0. And we've already solved that problem, so that's it. We're done. This is our condition. Yeah, that's C. And what I did was ugly. I don't really want to explain it since I actually don't know how to explain it. It's always a messy type of implementation, so we're just going to stick with that since that's a very simple problem. Okay, now we have D. D is very straightforward. You are given a bunch of sticks, for example, let's use the sample here. So 9, you're given a certain amount of red sticks, 9, 5, for example. Then a certain amount of blue sticks or green sticks, 1, then a certain amount of blue sticks, 2, 8, 5. And so you're given the lengths of each of these sticks. So this stick is length 9, this stick is length 8. And in fact, it's not just a single stick, it's a pair of sticks. So here you have 2 sticks of length 9, you have 2 sticks of length 5, you have 2 sticks of length 1, 2 sticks of length 8, etc. In one move, you can take 2 pairs of sticks of different colors. So you can't take both 9 and 5, but you can take both 9 and 8. Then you can make a rectangle with those sticks. And they, again, have to be different color. So this would be 9 by 8 and have area 72. And over all moves, you want to get essentially the maximum sum of areas over all possible pairings of sticks. You don't have to use all sticks in the pairing. For example, this one has 3, 5, and 4. The optimal answer is just to pair 5 and 4. Yeah, so all you need to print is the maximum area. You don't have to actually do the pairing. Wait, why did I get rid of the whole thing? Essentially, all you have to do is, it's like a very straightforward dynamic programming problem. So let dp of RGB equals the maximum area with where you've already used R red sticks, G green sticks, and blue sticks already. So in the transition is either you don't do anything or I'm not sure if it's actually necessary to sort the arrays. Yeah, actually no, it is. Yeah, it's necessary to sort first. So first you'll sort the arrays in decreasing order, so the biggest ones appear first. And the reason for that is because if you've already used a certain amount of sticks, then the element that you're at is going to be the highest stick that you haven't used yet. And the general greedy idea here is that you want to make as high, you want to use as many large sticks as possible. So that is the basic idea. And the transitions are, if it's possible, you can take a red and a green stick, and then it's R. So it's like, for example, let's call this the array A, the array B, the array C. So it's A, R minus 1, 0 indexing, times B, G minus 1, plus dp of R minus 1, G minus 1, B. It's the maximum of that, and what happens if you take a green and a blue stick, and you can also take a red and a blue stick. So you can take just RG, GB, and RB. And essentially that's how you do the transition. You just check those, and then I implemented it recursively because I feel like that's nicer to do. That may have contributed a lot to the runtime, but you know, C++ is nice in that regard. So yeah, that's essentially it. This is the transition. You compute the area. Whoa, sorry. You compute the area, and yeah. Then you just check everything you can do. And it's just a very straightforward DB problem. I guess it belongs on an educational round, but nowhere else. Okay. E is very fun to implement. Honestly, I predicted this wouldn't be fun at the beginning, and I was kind of right. This is just This is just not, there's no value in this problem. You just kind of have to do things. Okay. So the way E works is, I'm gonna have to figure out how to explain this. The way E works is that, I guess I'll just start with the problem. So you have a bunch of like, let's try and draw fire here. You have a bunch of like fire spells, you know, classic fire, and lightning spells. Lightning spells. Let's say, boom, lightning. Yeah. I don't know why I'm drawing these, but, you know, just for fun. So, you're going to cast all the spells in some order. So a fire spell does a certain amount of damage, and a lightning spell also does a certain amount of damage, but at the same time lightning spell also does a certain amount of damage, but at the same time it doubles the damage done by the next spell. Next times 2. So if there is no next spell, you just won't double anything. So that's essentially the way it works, and you want to find an optimal ordering for the spells. However, that would be too easy. So instead what you do is, you start with no spells. Then, n times, you either learn a new spell or forget, what is it? Yeah, forget a spell you already know. And then each time you want to recompute the maximum number of damage you can do with that change. So that's the problem. Yeah, that's the problem. So how do you do this? Well, intuitively you'll want to double the biggest things possible. Like, you'll just, yeah. And at the same time, you can also double exactly, so let's, for example, let's use some very nice variable names. Let F be the number of fire spells and L be the number of lightning spells. Then you get exactly L doubles. However, because the first lightning spell you use can't be doubled, you can only double L minus 1, I'll make it a capital L. Only double L minus 1 lightning spells. And then the other one has to be fire if one exists. Because again, the first one can't be doubled. So for example, if you, like, if this one is a lightning spell, for example, and you can't double this one, because like there's nothing before it to double it. So that's the way it works. And so the strategy here is you just keep a bunch of like sets. C++ does this nicely where you just use a set and then it'll let you get both the smallest and the biggest element. So that is nice. And let's say you solved it for some time, like after some number of spells being learned or unlearned. Then what you're gonna have is you're gonna have two different sets, the things that are doubled and the things that are not doubled. And we're going to say these sets are already built. And within that, we're going to have within each of those, we're going to have two different sets for fire and lightning. Then, let's say we, for example, learn a new spell. Doesn't matter what it is. at the beginning, we're going to put it in the not doubled set, and the key observation here is that, unless I get hacked, in which case I will be hacked, but I think it's true that, and I have an AC to support it, that after each operation, like only one of each of these will, for example, switch from being doubled to not doubled, and at most one of each of these will switch from being not doubled to doubled. So what you can do is, after each operation, to make implementation nice, no matter what happens, you'll remove one from the set of doubled fire ones, and remove one from the set of doubled lightning ones, if it exists. That is, you'll remove the smallest one from both of those. And then this one will go here, and this one will go here. Then what? Then you can kind of do greedy. As in, while it's possible to take a spell, that is, you have to have more than one lightning spell or more than 0 fire spells, then while it's possible to take a spell, find out the biggest spell you can take. So for example, if I go here, so if you can't take a fire spell, obviously you have to take a lightning spell. And if you can't take a lightning spell, obviously you have to take a fire spell. But if you can take both, then you look at the biggest one for both of them, and you take the one that's bigger, and then you move it to the doubled set. And essentially that's what this case, this code is disgusting, I'm not going to show it. But that's not what that's essentially what the casework is. And yeah. And you can do the same thing, just remove one from fire and one from lightning in both cases. That is, in both adding things and removing things. Then you just, yeah. And that is also nice because it means if you remove a lightning spell, for example, it reduces the number of things you can double. But since you remove these anyway, you'll check for that and recompute the answer efficiently. So it's only like you only do like, at most, I think 6 removes or inserts, which means like, because you have to remove it from one insert to the other, like 12 set operations or something. So it may not be exactly 12, but it's something on the order of like 12 log n. And then because you have n operations, you have n times 12 log n. So my implementation took 218 milliseconds, which means it's not that bad. N is only 2 times 10 to the 5th, and you have 3.5 seconds, which is quite high. So essentially this will work, even though it's a lot of technically unnecessary set operations, and you can make it easier with casework, or you can make it faster with casework. This is easy to implement because you don't have to do any casework on adding or removing. So that's essentially the way that works. That's my implementation for C. I hope you enjoyed my drawings of the elements. Or sorry, E, not C, not C. Not C. Yeah. Alright, F. F is a simple problem, but the solution is not simple. Unless I missed something. So you have a binary string, which is a string of 0s and 1s, except some characters can be question marks. And the essential idea is there's some value x. You want to change the question marks to either 1s or 0s to maximize the number of... No, that's not exactly accurate. What you want to do is you want to maximize the something. Let's say x equals 2. and then you have some extra zeros on the end. And then we'll set this to 1, for example. So what you're going to do is you're going to start from the left. And then for the leftmost contiguous subsequence that is together, where all the elements are the same of length x, so either 1s or 0s, you're going to count that as 1 and then move on. So this for example, this subsequence doesn't count for anything because it has a 1 and a 0. This subsequence does count, so it's 2 zeros, so you get 2. And then this subsequence also counts because it's length 3, and then this subsequence doesn't count because it's only of length 1. Or sorry, substring, I guess. That would be the right term. Because, for example, if you had a 1 here, you can't do something like that where you combine these. They have to be together. And so that's the score, I guess, for a string. And that's also the score for a value of x, where you can change the values however you want. So, I think, maybe I'm wrong, that if you have a, like, let's say x was fixed, right? So you have like 1, 1, question mark. Let's say 1, 1, 1, question mark, 0, 0, or 0. Then x equals 2. What you would want to do is you'd want to, like, for this, you need 1 more to make this work. So you'll attribute that 1 question mark to make this work. And then it's optimal to give the rest of the question marks to the next element. And it won't hurt you, essentially. So that will work fine. And then essentially you'll just do a greedy. But the issue with that is that the problem asks you to compute it for all x. So if you were to just do the brute force out for all values of x, it would take O of n squared, and that will not be fun. You will not be happy. So instead what you have to do is, like, be smart about it, I guess. And my way of being smart, which it turns out was not actually smart because it got 2 wrong answers, was first, well, let's go over this. So the sum of this series, this is totally out of nowhere, but the sum of like n divided by I for all I from 1 to n is O of n log n. It's like, it's not exactly n log n, but it's on the order of that. So it'll be like some constant times that. And there are a lot of proofs on that. One of them uses calculus. I've written another one in a blog that I will just link in the description, since there's no point to write it out now. I think it's good enough. So we'll leave it at that. So therefore, and the answer for an x is at most ants is less than or equal to floor of n over x, because like that's the amount of subsequences, that's the amount of substrings you can take. Like if x is 4, like you only have 6 characters, so you can only have at most answer is 1. So therefore the sum of all of the answers is floor of n over I, which is less than or equal to the sum of not floor of n over I, which is O of n log n. Now similarly, let me bring out another fact. The sum from I equals 1 to n of n over I over k. I'm essentially proving my solution's complexity before I actually describe what's happening. Is roughly equal to the sum from I equals 1 to n of kn over I it's about the same thing, equals k times n over I equals k O of k n log n. So we're going to move this down for now, but this is essentially the complexity of the solution I have, and I will bring it back later when it becomes relevant. So what you do is, my solution hinges on this. Let's say x equals 7. And you have something like this, question mark, 1, 1, question mark, question mark. And then you have something to the sides of this, and then something to the sides of this. This is never going to get you anywhere. Actually, for this to be true, first you have to do some things to the string. So, let's say you have question mark, 0, 0, dot, dot, dot. Right? If you make these ones, then it may hurt you in the future. But if you make these zeros, then it's just going to extend this one. So it's at least as good as making them ones. So if you have question marks on the end, you can make them into the value that they're next to. Similar, I mean at the beginning, not the end. But also at the end, the same principle applies. You might as well make these, for example, 1. Okay, and there's one other thing that if you have, for example, 1, 1, question mark, 1, 1, dot, 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 then if you make these zeros, it's going to cut the subsequence in half, or the substring in half. But if you make these ones, then it's just going to naturally make it bigger. So it's also okay. I made a face. Nice. It's also okay to it's also essentially okay to make these into ones. So if something is if a group of question marks is surrounded by the same value, then you might as well change the question marks into those values. So it's kind of cute. Yeah. So with these two observations, if we basically change the question marks to those, then we'll have a string that looks like this. It could, for example, start in 1, 0, 1 question mark. That doesn't really matter. It doesn't matter what it starts with because 0 and 1 are equivalent, except that they're not the same. So we're going to have a string that looks like this. So 0, question mark. So some number of zeros, some number of question marks, some number of ones, some number of question marks, some number of zeros, some number of question marks, some number of 1, etc. And it always starts with a non-question mark, ends with a non-question mark, and question marks are between two different things. So these are not the same. So that's the type of string we have. So therefore, with this, now we can claim this. If all of these are 2, so if we have a certain number of values that are if we have some number of values that are if we have 3 values in a row, all these question marks are next to this. Keep in mind we're going to have, for example, a 0 at the end of this, a 0 at the end of this, and then whatever happens. Wait. Okay, I figured out what's wrong with my solution. What does that do? What does that do indeed? So I'm pretty sure my solution is still possible, but it becomes even more complicated. Let's try something. So the essential idea was that if you have three elements together that are less than, let's say, the floor of x over 3, or let's say you have three elements together that are less than x over 3, then no matter what, these elements aren't going to get anywhere. I need to try this. Because if this works, then my solution will be possible, and if not, then like it won't work. So I'm going to, I guess I'll use some timestamps to like allow you to skip this part, since this is me verifying my solution right now. On B. How does this work? Okay, so it's not necessary here. Bad if on. This may time out. If it does, I'm going to be sad. May also get runtime error, actually. Okay. Why is that? It's not on -1. Nice. That was basically instant. Okay. Just told me that now. Okay, so not sure if not sure if this works. I think there are cases where it actually invalidates my solution. So I'm going to okay, if I edit this, it's going to take like 5 hours to process, so I'm going to figure this out. I think my solution is invalid, technically, for F, so I'm going to see how to fix that. For now, don't trust what I say yet. Although my general idea was that you could ignore most of the elements that have size less than x over 3 and then do some casework for the ones that do. But I don't think that actually works. So there's probably a different solution that may be simpler, or you could make mine work. Either way, it's going to be annoying. Let's say that. So yeah, that's it for this edge round. I like the observations for F, but then the implementation was just ugly. So although I'm not going to complain about it, since the solution might be actually different. So these are essentially my solutions for A to E. I basically didn't even look at G, because it's not really, like I didn't have enough time. Let's see. Wow. So this guy has been trying to drop his rating so he can get very close to Grandmaster, I guess. Now he actually won this round by an enormous margin. Jeez. Well, I guess that would be that. Even though we only got 5, our rank actually isn't that terrible. So, unless there are fewer people, I guess. Yeah, that is about it. Okay. I hope you enjoyed watching me, I guess, struggle in F and the rest of the implementation. Yeah. Okay, see you guys.